Okay, we'll come back to it. So let's get started. So I was reading the news today, and this is a very interesting news article. AI boom could add $16 trillion to the markets, but workers may have to pay the price as 90% of the jobs may be impacted. This is, I think, yesterday's article, not today. So what they are saying is, AI impact on S&P stocks, market cap, Morgan Stanley predicts 16 trillion boost to stock market, but this could raise the market cap by 30%, which is huge. Agentic and embodied AIs. And the retail and the transportation sectors will see a significant gain. Retail, obviously, right? You will see robots at the retailing ends, right? Especially in the big supermarkets. Transportation as well. However, AI adoption could impact 90% of jobs requiring workforce adaptation. So this I always wonder, what if all the jobs are taken away by robots? Now who is going to pay the robots? Right? Who is going to pay the AI? Because there will be nobody to pay the AI, right, if all the jobs are taken. So it's kind of not clear that how will it add 16 trillion if there's nobody to pay for that. But anyway. Okay, so inspired by this, I've changed the course plan a little bit. So I've moved the quizzes up, and presentation I thought then we can bring it down. Maybe I'll bring it down to 5 and 15. Don't know, but something like that, something in that range. And so we are going to have. Okay, let me announce a quiz. Huh? No, I'm announcing right now. So you may have a quiz on neural networks. So to understand everything about the neural networks, forward and backward propagation, sometime in the coming 3 lectures. Right? May or may not have. It depends on whether we are able to get our acts together or not. But yeah. So what has been brought to my notice is that some students are copying in homeworks. And these homeworks are like, very trivial things, very like less than 1 mark each. And some students are still copying. So I did not announce the honor code before, so let me just formally announce it. It's applicable to all components, homework, assignments, exams, quizzes. Copying and collaborating, or use of any other unethical means for doing assignments or quizzes. So this sort of requires quizzes or homework, right? Or exams is not permitted, okay? And one of the terms that I often get is, oh, sir, I was inspired by this student and therefore, my code is looking very similar to that student's code. He's my friend, I was talking to him, I was inspired. No such inspiration is allowed. Okay? You cannot be inspired. Discussion is okay. You can discuss with your fellow students because 25% of your learning comes from discussing with fellow students. So if there's a homework or there's an assignment that's given to you, discussion is perfectly fine as long as you keep the discussion at the level of algorithms and pseudocodes. Right? So what algorithm do? I do a binary sort here, or I do a binary search here, or I do, ternary search here. That is okay. Or you can discuss what's the problem with this algorithm versus that algorithm. What is not okay is having somebody look at the code that you have done. That is completely, even having a look at it is not okay. Okay? And, we get some reasons. Oh, sir, I just, wrote it and it's in my directory. And this directory is on some server. And I didn't know how somebody copied it from there. Right? It is your responsibility to protect your code. Okay? If somebody copies it, we cannot figure out whose code is it and who copied it. So both of you will get equal penalty. It's not our job to figure out who copied whose codes, right? So if you have a Unix system where you put your code in, there's a command called chmod, right? So that is your friend. Rest The other friend is OpenAI, right? You can ask ChatGPT how to use it so that your files are not accessible to other students without your permission. Okay? And yeah, in general, whenever in doubt, you apply the principle that use of internet code or ChatGPT or any other AI tool is not allowed unless explicitly stated. Okay? So the way this course is organized, we are going to actually allow it in many cases, right? In many assignments, in homeworks also we would allow it. But just to be on the caution, if I've announced it in the class that you can use ChatGPT for this particular homework, but the homework statement doesn't say it, you just raise a flag. We'll update the homework statement saying that ChatGPT is allowed for this homework, or OpenAI or AI tools are allowed. That's okay. But I think both we and you also need to err on the side of caution, just to make sure that everything is kosher. Okay? Okay. What happens if you violate the honor code? Okay? And this is something very interesting, There's a student who has come to me, sir, please don't give me a D grade, give me a F grade. Right? The person violated the honor code. Oh, D grade is too harsh. I want to punish the students for violating the honor code. I don't want to punish the next instructor for, not doing my job properly. Because that student was like maybe a core course, and that student would have to register in another course. So that I will decide whether it's a F grade or a D grade or a disco and a disco or a negative mark in that component. If you are cheating in homeworks, then entire homeworks can get negative, or you can get negative for that specific homework. But that will look at the severity of the offense and will decide on the case-to-case basis. Okay, that prerogative lies with me, not with you. Okay, harsh or no harsh, that is my decision. You cannot question that. So if you don't want to get into those discussions, better to follow honor code. Okay, it's not a trade deal that we are making that you make this concession and you make that concession. No, it's not like that. So it's something which is very important. And other important thing is you will not know until the very end of the course. So you may have violated in some homework or some assignment from this class onwards. In the previous classes, the violations are there. I'm going to treat it a little leniently. So you're not getting a D grade or an F grade for that thing. But yes, you are getting some negative penalties, those who have copied. But this I don't want to announce during the middle of the course, okay? Towards the end of the course, it will hit you as a surprise if you've done this. So be very clear about this. Better to follow the policy of honesty. And, many times students get stressed out. Oh, I'll get this, get that. Don't worry, it's okay. We have moderations. So we look at everybody grade. The whole department looks at it. And if it is unfair, they will tell me that, oh, this is unfair. So, you cannot do this. So, don't worry about that. That's our job. Your job is to just do the best you can, and it stops there. Okay? So, yeah, the slides will be uploaded. So just take care of this. Yeah. Well, when you remind me of the honor code, I'll remind you of the honor code. Okay, let's do it this way, right? So, whenever I see an honor code violation, I'll just flag it up again. It doesn't mean I may flag it up, okay? So it doesn't mean that every time we are going to do it, but yes. Fine? Okay. Any other questions, comments on this? Something that you did not understand?
The last homework that you gave and the argument that was attached, the Adams prop that was implemented there, without biasing, it was the results were like 10% accuracy and all.
Okay.
But when I did biasing, it was comparable. So, I wanted you to know that the article was not complete enough.
The statement, the assignment statement is not.
No. The article that was attached to study the different optimizer strategies. The rest three were
that was okay.
The Adams prop one had some problem. I implemented it exactly the same way, but without biasing because it was like motivated from Adams. So like biasing was there in Adams, but not in Adams prop. So when I was not doing biasing, according to the article, like the whole mathematical statement that was given, it was giving like 10% accuracy only.
I see. How about others? Are you finding something similar?
Yes.
Okay. So what did you implement then? With biasing. Okay. So can you send me an email? You can send me an email with exactly what's the issue, and in your homework statements, have you written all of that? In your homework submission, sorry.
We have already mentioned it on the other.
Huh.
You won't get penalized if you use bias prediction.
I see. That's okay. That's fine. That's okay. But you can send me an email exactly what the issue is, and yeah. So yeah, how did you find the homework? Huh? You are seeing the difference after fixing the Adam problem. Then you are seeing which method is the best. Huh? Adam and RMS are kind of similar. I see. Everybody is finding that? No? Yes. Huh?
There was one case EMS graph that was not working fine.
One case meaning?
There were 4 algorithms, right?
Huh.
Only the EMS graph was not giving good results.
Achha, other results are comparable. The graphs were exactly overlapping with the loss and the error rates.
Almost similar.
Huh?
Almost similar.
Almost similar, only EMS graph was not working right.
Not really. Oh, interesting. Okay, how many people are actually finding the other 3 algorithms not similar? They are behaving differently. I see. Okay. So maybe it makes a difference when the problem is a little more complicated, right? It's this is a very simple network, right? This is the early days of, neural networks, the convolution neural networks and all. I see. So you are saying that which one is not good?
EMS graph.
AMS, huh? I see. And the RMS, the Adam, and the third one? Huh? Momentum, classical momentum. But how about the parameters? Like if you tune the parameters, does it change? Adam has these 2 parameters, beta 1 and beta 2, and the other algorithms also have those parameters. What is the impact of those parameters? That's okay. This is to get you started, no? You can submit what's allowed, asked you, but you could experiment with changing those betas and see what happens. The whole point is, this is more like a research course, right? So a lot of learning happens by your own experimentation. So we are doing it so that you can actually, we are forcing you to actually come to a stage where you can do experimentations on your own. So that you can do, right? If you have something, I'll be very happy if you want to make a presentation or something that you found. So please let me know, okay? If you find something interesting that, if I choose this as beta versus that as beta, this is what happens and this is how. Because, deep learning, that's a big problem that, even if you speed up the algorithms, convergence rate by a factor of 2, that's a lot of, that translates into, vast improvement in model performance on one hand. On the other hand, if you're thinking of training like GPT-5, a lot of money getting saved, right? Because you can, do with much less hardware and much less electricity to train these models. Okay. Any insights that you'd like to share? Anything? Anybody who has done some experiment? Yes.
I have to share about the penalty for past offenses.
Huh.
But in homework, when you mentioned we are free to use AI tools.
Huh.
So we assumed it for all.
Yeah, but your prompts cannot be identical, right? 2 students cannot use identical prompts, and then therefore, even if they use identical prompts, their output cannot be identical. Because AI keeps on changing, it keeps on evolving. So that's okay, that's fine. That's fine.
Copying from AI tools, then you are not, it's not allowed.
Yeah, but past you don't worry. Past you have to only worry if you copy it from a fellow student. Okay? If you copy it from a fellow student, yes, you are getting some negative marks. Or if your AI and your fellow student's AI gives you the same output, right, which is highly unlikely, the probability of that event is very small. But then you are, you have to worry. Okay, you have to work extra hard for the rest of the course. Okay, I've created a list of papers. So make your teams, and the teams that are going to do the presentation are going to be the same as teams that are going to do the homeworks. And we are going to do all the 3 homeworks. I would like to have the same teams. So choose your teams, discuss with your team members, discuss about their audit or withdrawal status, and or inclinations for audit and withdrawals, and based on that decided. Make a commitment to your team members, whatever it is, right? Are you going to audit or withdraw? And we are working on the assignment statements to get it out soon. today, hopefully, I'll be able to release the list of readings along with the tentative dates of presentations. And, I'll ask you to fill a form where you're going to set your team, and then with your teams, you're going to select which of these papers you're going to read. So that's where the fun part will come in, right? A lot of it is advanced readings, and a lot of these papers that I've also not read, so at least some of them. So then, it will be fun to kind of, go through it together. Yeah. So pay attention to that. So let's come back to CNNs. Again, today's class will be mostly, I think, kind of like a review class for people who have done machine learning. And this would have sort of been covered, but just for the sake of completeness, there are many students who have not done machine learning at IIT Delhi. So for them, I think this will be good. So as we talked about, deeper networks have more expressive power. They can, learn variety of different things. They can represent better models, but it's hard because of vanishing gradient problems. So how do we actually design a deep network that can actually learn something meaningful? And it turns out that for imaging problem, there's something called a convolutional neural network architecture. This is very effective in learning, neural networks. So we are going to discuss in the next class, in today's class, these convolutional neural networks, and hopefully, we'll have one of the presentations next week on CNNs, right? Some advanced CNN architectures. So what are the key ideas in CNN? But before we go there, let's look at a little bit of history. CNNs are not new, okay? The first paper that I kind of looked at was 1979 by Fukushima. And neurocognition, he called it. And this was, the name neural network is really, very appropriate because it's inspired by how, at that time we were beginning to understand how the brain works, and we discovered neurons and we discovered interconnectivity of neurons. And inspired by that, especially our visual cortex, the architecture of our visual cortex, he came up with this particular architecture. So what happens in the visual cortex? Our signal comes from our eyes, retinas. There is an optic nerve that carries it to a visual cortex. And in visual cortex, there are different areas, like V1 area. So if you read some of the papers, actually early papers of neural networks, they're actually trying to imitate how the neurons behave. So there's an early visual area called the V1. And that visual area processes something very simple features of the image that's being formed in the eyes. And those could be things like, the direction of the lines, the directions of the edges, and stuff like that. So if you have edges like this, then some neurons in your V1 will start getting activated. If you have edges like this, the other way, different set of neurons will start getting activated. So V1 is just very low level features. And then there's the area called V2, V3, V4 and so on. And as we go to these higher level areas, the kinds of features it recognizes becomes more and more complicated. And inspired by that, he came up with this architecture of neural network and simple cells and complex cells. And essentially this picture that I directly took from his paper talks about, there is input layer, and then from there he is getting to the next layer, and the activations here at the next layer is a convolution of the activations at the input layer, and layer by layer you get the next layer activations by doing these convolutions. So this is again a picture from that paper, and there you can see here in more clarity that this is one of the units at the next layer, and it is dependent only on a window in the previous layer, and then it combines it in a particular way. Similarly, another unit, again the window of the same size, it combines it in a particular way using these convolution weights, and these weights are shared across all the different voxels or all the different units. And interestingly, digit recognition problem, that MNIST that has been there for quite some time, is still trying to do that back in 1979, still trying to do digit recognition, and it's reporting the performance on that. So anyway, and then come back, fast forward 2012, ImageNet paper, AlexNet, and this I talked about in the last class also. It jumped its sort of ImageNet classification, it led to a significant improvement in the performance, and this was the actually turning point. So 1979 to 2012, right? So 30 years, 33 years after the first CNNs, then we had something which actually started getting adopted. But anyway, so what are the key ideas in convolutional neural network? It's mostly used for image classification and possibly also looking at the speech signal, and it's one of the key foundations of deep learning. The first idea is, of course, you have to have a deep network. Second thing is, how do you learn the weights, right? And how big networks you should have, how many units you should have in the intermediate layers. Now, if you have too many units in the intermediate layers, you can, of course, the network becomes more expressive. You can learn many different kinds of functions. But the number of weights you need, if the units are fully connected, also becomes very, very large. It's like quadratic in the number of units. So if U1 units and U2 units are there in two subsequent layers, then the number of weights between them would be U1 times U2. So that leads to a weight explosion, and that also makes it harder to learn. But this is solved by what are called convolutional layers, and in the convolutional layers, somehow we use the weights across different units. So we'll talk a little bit more about this. And then the third idea is, instead of using the classical sigmoid type activations, we use what is called a ReLU activation. So these activations, the sigmoid, would lead to vanishing gradient problems when you are here. But ReLU activations, which are like this, at least if you are in the positive side, in this range there will not be any vanishing gradient problem because the slope is 1. But here the slope is 0. So here there will be a problem called the dead units, the problem of dead units, because if you are in this range where the slope is 0, then the gradient does not backpropagate anymore. So those neurons or those units where you are in this particular range will not get any gradient, so you will not modify those units, the weights for those units. And that leads to the problem of dead units. But that is not really a problem because we are looking at the convolution layers. So the weights are shared across multiple units. So even if for one particular unit the derivatives are 0, but then since the weights are shared for that unit, if you look at for that weight, you can look at a different unit, and therefore you can change the weight. So this will become a little clearer as we talk about it. And the final idea is that of max pooling. What happens in max pooling is, you look at an image, for example, and you look at the pixels here, and from here you look at the max. So you look at a window size in the image, and whatever is the output there, you take a max and propagate it forward. So essentially, for example, if you are doing edge detection, you have a convolution filter that is somehow finding out the edges, then if you take a max, then those edges will get propagated to the next layer, and the unnecessary details will get stuck, will not get propagated. And then, of course, you have to figure out how to do backward propagation with that, and that can be done. It's not really that difficult. So this is how a typical architecture looks like. So you have the input here. An input could be an image. It could be a 1000 cross 1000 image, but it could also be a colored image. So it will be 1000 cross 1000 cross 3, right? If it's and then you have a convolution layer, and then you have a ReLU activation. Now, when you convolve this image with a convolution filter, you will get another image of similar size, maybe slightly smaller size, but of almost similar size. But you don't have one such convolution layer. You will have multiple such convolution filters. So here you see this depth. So you have start with 1000 cross 1000 cross 3 image. You can go to 1000 cross 1000 cross 16 images at the next level, because you are doing multiple such convolution filters. Now from here, you go to the next layer again. Maybe you do some kind of max pooling, so the image size becomes half of the previous image size, because if you're looking at a 2x2 window, so then you're taking the max there. And then you see the increase in the number of filters. So you get many more layers, and keep doing that until you reach to the end, where this becomes extremely small. It could become like 5 cross 5, and the number of layers becomes very large. This could become hundreds or thousands as well. And then finally you flatten it, and you have a fully connected layer, and then you try to predict through the normal logistic type, cross entropy functions as to what the output is. So this is in principle the general architecture of neural networks. Of course, there are many different types of neural networks that involve CNNs, and they're all architecturally, small differences are there. But this is the basic idea of a convolutional neural network. Okay, any questions on this so far? Okay, good. So, what is a convolution? So let's say this is my input image, and let's look at only grayscale image. So this is one plane only. So this is my image size. Now the voxel or the pixel values are like, the intensity values, the grayscale intensity values there. Okay. So now if I apply a convolution kernel, and let's say it's a 3x3 kernel. So I have these convolutional weights for this kernel. So these are the weights that are going to be learned by this layer. Okay. And what happens is, let's say you want to find what is the value, and from here you are going to get some output of that particular layer. And what should a particular output value be? So if you want to look at this particular pixel, what the output should be, you look at a corresponding block centered around that pixel in the input. And then you multiply it with the convolution weights and then add them up. So we multiply -1 with 3 here. So you take this -1, multiply with 3. You take this 0, multiply with 0. You take 1, multiply with 1, and so on. And you add all of these numbers, the products, and that will give you the final number 3 here. So, this you keep doing for different points here. So you can go to the next pixel, again redo the same thing, shift this block a little bit, and then do the same thing, and through that you can compute the output. Okay, and then you can apply the activation functions. So then you can apply the activations, and then you can get the final output. And then final output. Okay. Any questions on this so far? Yeah.
Is this really convolution or is this cross correlation? It is something that So is this actually convolution or is it cross correlation?
What is the difference between the two?
We are just multiplying it by element wise. So that's not actually convolution. It's just the past name that they are using.
Okay, so this is there to sort of help you understand simply, because imagine this particular, matrix, just invert them, flip them along x and flip them along y direction, right? So then it will become convolution. So, but if I flip it, then it will be hard to visualize what's going on. But actually it is convolution. So let's look at, everybody has done signals and systems? Anybody who has not done signals and systems? Okay, so maybe just remind me if I do not, I'll post a reference on convolution. We'll very quickly just define convolution, what this is. So, and then we go on. So let's say there is a signal called x of t. Okay, and from this we want to get an output signal y of t. And we have a convolution kernel h of t, which is also a signal. Right? So x of t is a signal. X is a signal. What is a signal? It's not. You can think of it as a function that is mapping the time into a real number. So it has a value at every point in time. And there could be continuous time signals where t is continuous, a real value, or you can have discrete time signals where t is taking integral values. So let's say it's a discrete time signal and t is taking integral values. So now you can think of it as if this is t, this is x of t, and it can take some values like this. Okay, and there is a convolution operator h of t, which could be as simple as this. This is t, this is h of t, and it's a discrete time. So at different points in time it has integral times, it has these values. Okay, so we write it as, now we somehow apply this convolution h to x to get the final output, which is y of t. It will give me some final output. So I'll just write down the formula. So what is the y of t? What is the output? Is summation tau is going from minus infinity to plus infinity, x of t minus tau and y of h of tau. Okay. So there's a lot of theory behind this, right? This is one full semester's course just discussing this, right? This convolution operator. We cannot spend that time here, but essentially you think about a very special case of h of tau, which is like this. So this is t equal to 0, and let's say this one, right, minus 1, and this is 1. So it is 1 at t equal to plus 1, minus 1 and 0, and it's 0 otherwise. Okay? Now, the way to think about this is, you have a signal x of t, and we are modifying this signal. So far we talk about, functions, right? What is the function value at a particular, f of x, right? If I give it an input, x, what will be the output of my function? That's what we are used to. But here we are going into a second level, a second order thing. So I'm not looking at individual function values. I'm looking at a function to give as an input. And what I get as output is another function. So I give this signal or a function to my system, which is given by this convolution operator, and I get an output which is again a function. Okay? So think of this as if, this is like your amplifier in your concert that adds echo to the sounds. So you give it a sound as an input, because sound is not a value, it's a function that changes with time, right? So whatever you are speaking in the mic, after I am speaking in this mic, is a sound, and that I give as an input to the system. System does something, it amplifies it, adds an echo to this, and that gives me an output. It can also do some kind of, noise cancellation, it can do some kind of, what is it called, equalization, band equalization and stuff like that. So, yes, so now how is this h transforming my x to give me y? Right? How is it transforming my input to give me the output? Let's look at this very simple case where your h is just a 3-valued thing. So, yeah, it is non-zero at only 3 places. So what will it give you? So what will be the y of t? If I look at tau, which is greater than 1, if I look at this formula here, so tau which is greater than 1, then h of tau will become 0. So I don't have to sum after 1, right? If tau is bigger than 1, this will be 0, it will not contribute. Similarly, tau less than 1 will also not contribute. So what will contribute? Only tau between plus 1, minus 1 and 0, these 3 values. So what I get is x of t minus 1 plus x of t plus x of t plus 1. Right? If I make it 1 by 3, then this will become 1 by 3 of this. Right? In other words, this is a moving average filter. I'm looking at the signal x, I'm taking 3 values, current time, previous time, next time, I'm doing a moving average of this. This is one example of what convolution does. But, there can be many things it can do. It can find the derivatives, it can find the edges, and all kinds of things. Okay, any questions on convolution? So those who are new to convolution, I'll put some references. There's a very nice course by Oppenheimer. It's the video lectures are available, and his book is also, I think, freely available. So you can look at. I think what you need to do is just look at the discrete time convolution. Okay, don't have to go into the continuous time convolution. And so I'll post it as optional reading material. And you can do some problems. I think if you solve some problems, that would be helpful. Yes?
So we are not flipping the kernel, right?
It's just a convention.
Yeah. And that's the thing. If you are flipping it, we just change the value. It would be the same for matrices. Like if I just take the mathematical function, it would not be the same. The cross correlation and the
flipping now, we can change the values and do the same.
No, I don't understand what you're trying to say. So here in this example what I have drawn, it is actually not this, it is actually x of t plus tau and h of tau, right, instead of t minus tau, right, in that example. But, I can just think of this as, I could just flip the h of tau and then it will become same as that. So, what is your comment?
Even if we are flipping here in the matrix sense, we can change
There are no
the values.
matrices here. Okay, you're thinking this as a matrix, the input as a matrix.
Correct.
Okay?
So we can change the kernel.
Huh.
We can change the values and do the same again.
For this particular kernel. Oh yeah, this is a symmetric kernel, yes. It is a symmetric kernel, so even if you flip it, it will be the same thing. Yes, you are right. But in general, it need not be symmetric. It need not be symmetric, yes. So here, for example, what you see in this particular kernel, this is 1, this is also 1, this is minus 2. Wait, this is not symmetric.
No, I'm saying even if you are just flipping it, just change the values according to it.
Yeah.
Then it would be the same. There would be no
It is, flipping is same as changing the values.
Yeah.
You can say it like that. So, yeah. Does that create more confusion or it's kind of okay? Huh? You're okay? You're fine? Okay. So, 2D convolution. Right? So now we have x and it's a function of two variables, right? So right now we talked about a signal which is a one-dimensional signal. But in an image, I can think of an image as a two-dimensional signal. It has an x-axis, it has a y-axis, and then the value for each value of x and y-axis. So I can think of it as if I have x, I, comma, j. And from here, I am going to y, I, comma, j. And my convolution kernel also becomes a two-dimensional convolution kernel. Okay? So how do I get to the output from input? So y, let's say t1 and t2. I'm going to just use t1 and t2 equal to summation tau1 is going to from minus infinity to plus infinity, and summation tau2 is going from minus infinity to plus infinity. X of t1 minus tau1 and t2 minus tau2, and h of tau1 and tau2. So this I write it as y t1 t2 is x t1 t2. Convolution I represent it as a star. So if I convolve the signal x with h, I get the signal y. Okay? Okay, what can you do with convolutions? Here is an image. I remember I talked about 1D convolution and I talked about the moving average filter. I can do that in two dimensions as well. I can do a 1 by 9. So my convolution kernel H could be 1 by 9, 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 and 1 by 9, and 1 by 9, and 0 elsewhere. Okay, so what do I mean by this? This number is h of 0, 0. Okay, this number is h of x. X is this axis, right? 1, 0. Right, and this number is h of minus 1, 0. And this number is h of minus 1, 1 plus 1, right? So this, I'm thinking this is my, y-axis is my x-axis, right? Two axes, okay? And this is what? This is h of 1 comma minus 1. Right? So if I apply a filter like this, I convolve, maybe this is like, if you look at this, I think this is a much bigger filter. So it is not just plus minus 1, it may be going from plus 10 to minus 10, and then y also plus 10 to minus 10. And if you apply this, basically every pixel here is a moving average of a window of pixels in the previous image centered at this pixel value, and then I take the average of that. So you see that initial picture that I drew, that my input image, I look at, to get a particular point in the output image, I look at a window of size W in the previous input image, and I apply this convolution kernel weights, and then I add them up. Right? And if I flip it, but I think flipping is same as writing this matrix differently. So I'm going to use the notations interchangeably, whether we flip it or not. It's about the same. It's just a convention thing. Is that clear? Okay. What else can you do? So what if we apply a ReLU after? Yeah, we can apply a binarizing filter, but we can also apply a ReLU. Numbers less than a particular threshold go to 0, and numbers greater than threshold, they just keep that. Right? So you can get, like in this case it's binarized, it's a binary image, but in general you can apply a ReLU filter after this. So this is how the image will look like after you binarize it. Okay. What if your convolution kernel is something like this? So this is H. Or I can just represent it as x comma y. Sorry, that's a bad notation. U comma v, yeah. So it's 0 everywhere except this particular point. So what will it do? So let's look at the previous example. So if I have some x of t, let's look at 1D. And my h of t is 1 for t equal to 1, 0 otherwise. Okay? So this is my x of t. It could be any signal. And what is my h of t? It is 0 everywhere. At t equal to 1, it is taking a value of 1, and it's 0 everywhere else. What will be y of t? Is summation tau going from minus infinity to infinity, x of t minus tau, h of tau. Okay. So now, when is h non-zero? Only when tau equal to 1. So I can just keep that value, everything else goes away. So this becomes x of t minus 1. So what have I done? I have shifted the signal in time in one dimension. This is exactly the thing that is happening, right? Along the x dimension, you are shifting in time. So if you convolve this even in y dimension, it's like again the delta, same h of t, which is 0. So if you convolve it with this function, along y it will be identical, along x it will shift by 1 pixel. Yeah. It depends on the convention what you are using. So if you are using the t minus tau convention, then let's see.
So for the 2D case.
Yeah, for the 2D case, again you can see. So y of t is x of t minus 1. So it shifted right by 1 pixel. Right? If you use a convolution, formula, if you use the other cross correlation type formula, then it will be shifted left. But right now we are using the convolution formula. Okay? Is clear? Okay. Blurring. This we look at it, right? This is 1 by 9 times all ones. Yeah. Edge detection. Okay. How do you do edge detection? So here is an image of a dog, and you want to get an output which sort of is a value is higher wherever there are edges. Yeah. Let's say I want to do horizontal edge detection. How do I do that? What filter do I apply? What convolution kernel do I use? Okay, so horizontal. Yeah. Okay, so if I have an image, then here, for example, in this image, my horizontal edges will be here, right? Here, here, and maybe somewhere here, right? These are my horizontal edges. Maybe here, maybe here. Okay? Okay, so how do I do this?
Pixel difference row wise.
Yeah. So what will be my edge? So how do I do edge detection? What is the property of an edge? If I look at a signal, if I think of this image as a signal, right? Think of it as a one-dimensional signal. And I just scan through this image like this. And that is my signal changing. I can think of this as my time dimension, right? Or my x dimension, and how is the image value changing? So where will there be an edge? Let's say I'm looking at a vertical edge. So the vertical edge will happen when the value changes too quickly from the previous time point. The next time point the value changes too quickly. Similarly, horizontal edge will appear when the value along the y dimension changes too quickly. So to find the edge, I have to look at the rate of change of the values. How do I find the rate of the change? I look at the previous value and subtract it from the current value. So if I want to construct, let's say, xt and subtract xt minus 1 from this. So this is going to look at the rate of the change. So I want to find a horizontal edge. Then what do I want to do? I want to subtract. So maybe along the x I want to just keep 1. This I keep 0, and this I do minus 1. Right? So what it will do? It will take the average of the 3 along the x dimensions and subtract it from the same average of the next pixel in the y dimension. Right? So this is going to do a horizontal edge. Okay? Here they have just done a simple filter like this. Okay. What if I want to do, edge detection is irrespective of whether it is a horizontal or a vertical edge. Right? I want to even do slanted edges. So I take the image, I do a horizontal edge detection, I do a vertical edge detection, and I just take the sum of the squares of those, or just do some kind of addition of that. Or I can design a convolution filter, which sort of, 4 either minus 1, minus 1, minus 1, minus 1, minus 1, like this. 1, 2, 3, 4, 5, 6, 7, 8. So maybe this would be 8. A filter like this. Take the current value and subtract all the neighboring values from it.
How does this detector?
Huh?
How does it detect the diagonal?
I don't know. Does it?
It actually sharpens the image.
It will sharpen the image? Okay, it will not do the edge detection.
Yeah, I think it's just for finding the brighter points.
Brighter, relative to the neighborhood. Yeah, okay, so this is a bad idea for edge detection, right? This is for something else. But you get the point, right? So the reason we are discussing this is, you can read about convolution. This whole life you can spend on just doing convolution. Many people have spent their lives. Even today they can do it. Right? How? Why? What are the applications? Anybody can guess? Yeah. Yeah, but I'm talking more conventional, traditional applications. In machine learning, yes, you can do without convolution also. You just throw in a convolution kernel without even knowing what happens, put some code in, it will give you some output. As long as on your training and test data you're doing well, you don't care about the rest, right? This is how typically people do it. But if you're a researcher, then you have to understand this. But I'm thinking conventional application. Where would you, apply this in conventional engineering? Basically, all kind of signal processing. 6G, we're talking about 6G. You're sending some, signal over a mobile network or over airwaves. You're modulating your sound waves or some data over that, and you're receiving at the other end. You want the data to be error-free. So you want to develop codes that will, allow you to multiplex multiple signals on the same airwave and also reliably detect when you decode it and without any errors with low latencies. So the physical layer of the mobile networks would still involve a lot of signal processing that could be done by these convolution kind of operators. So you can still, lead a life, thanks to the mobile phones, just doing convolutions. But we are not getting there. So what essentially I want to say is it's a very rich operator. This convolution is a very rich operator. And a variety of things you can do with convolution. So we're talking about edge detection. Hey, this was the edge detection. Well, except there were zeros here, but okay. And this is another filter which is edge detection, right? So you can sharpen. Yes, this was sharpening one. I don't know what's the difference between the two, but anyway. So you can sharpen, you can do various kinds of things with applying different types of convolution kernels, depending on what you want. Right? So identity, edge detection, sharpening, blur, different types of blurs, and then many more higher order filters that could be applied. So what happens in CNNs? We say there are two ways in which you could do this. You could say that, okay, I want to find out where, number 1 is written. Let's say looking at the digit recognition problem. I want to find this out, I want to find that out. You design special filters like this. At every layer, you define multiple filters. You spend your life designing those filters. And then in the end, you put in neural network layer saying that, okay, now that I've processed my input image, generated these features, now I'm going to do a machine learning to do the prediction. That is the conventional way of doing that. But what you could say is also that, I don't know how to learn, how to design these filters. I'm just going to assume there's these filters like this, and I'm going to learn these filters from the data. And that's how the convolutional neural networks came in. So if you have a filter that is giving you from this input to another output image, those filters are the weights of your convolution layer in the neural networks. And these weights you are going to learn by doing the back propagation, by starting with random weights and doing the back propagation, and finally your network learns these weights, and then hopefully it's going to predict well. So that's the basic idea of convolutional neural networks, that instead of designing these filters manually, we are just going to get the network to learn those filters. Okay? So we'll stop here and we'll continue next time. I'll send out the reading list. You can, select your part.